Somewhere in the Milky Way tonight, a black hole is moving through the dark, unattached to any star, invisible except for the way it bends the light behind it. That is not a rare event. Astronomers estimate that our galaxy alone contains roughly 100 million black holes of stellar mass, the collapsed remains of dead stars. Most drift silently through interstellar space, far from anything they could affect. In 2022, astronomers using the Hubble Space Telescope confirmed the first one ever measured in isolation, drifting about 5,000 light-years away. Based on that discovery, the nearest one to us may be as close as 80 light-years, astronomically speaking, right next door. None of them are headed our ways. But it is worth asking, what would it actually look like if one were? Let's walk through it not as prediction, but as a physically grounded thought experiment. On screen, distance from the Sun 1,000 AU, time to arrival 95 years. At 1,000 astronomical units, roughly 25 times farther than Pluto, our approaching object would still be invisible to any telescope. A black hole this size emits no light of its own. The only clue would be gravitational, and gravity, even from this distance, leaves a trace. Astronomers regularly track the Sun's position with extraordinary precision, watching for the faint wobble caused by orbiting planets. A sufficiently massive, sufficiently close intruder would add a wobble of its own, a slow, unexplained drift in the Sun's motion, and a matching pattern of light bending faintly around distant stars as it passed in front of them. This is called gravitational microlensing, and it is the same technique astronomers already use to find rogue black holes today. At this distance, our object would already be brushing the inner edge of the scattered disk, the sparse outer shell of icy bodies that marks the true boundary of the Sun's gravitational reach, far beyond the 8 familiar planets. Objects out here are only loosely bound to the Sun in the first place, and a passing mass this large would begin nudging some of them onto entirely new paths, decades before anything closer to home was affected at all. On screen, distance from the Sun 494 AU, time to arrival 47 years. By the time it reached the neighborhood of Sedna, one of the most distant known dwarf planets, out past the Kuiper Belt, the effect would be unmistakable. Sedna's already elongated orbit would begin to shift in a way that no known object could explain. At this range, the object remains impossible to photograph directly. What gives it away is still the warping of the stars behind it, faint, shifting distortions that trace out a path heading unmistakably inward. On screen, distance from the Sun 200 AU, time to arrival 19 years. As it crossed into the outer solar system, the ice giants would begin to respond. Neptune and Uranus, both roughly 30 astronomical units from the Sun, would show small but measurable shifts in their orbits, nothing dramatic yet, but enough for observatories on Earth to confirm what the data had already suggested. By now, humanity would know with 2 decades of warning that something massive was on its way. On screen, distance from the Sun 52 AU, time to arrival 5 years. At the distance of Pluto, the object would finally become detectable in a more direct way. As it passed in front of background stars, its gravity would bend and briefly brighten their light, a lensing signature clear enough to confirm beyond doubt that this is a black hole and to estimate its mass. On screen, distance from the Sun 50 AU. At this range, the black hole and the Sun begin to notice each other in earnest. Both are now responding to a shared gravitational pull, curving slightly toward one another. The entire solar system, Sun, planets, and all, begins to drift in response, like a small boat caught in the wake of something much larger passing by. On screen, distance from the Sun 31 AU, time to arrival 3 years. Neptune is the first planet to be seriously disturbed. Gravitational encounters like this one tend to end one of 2 ways for a planet: capture into a new, tighter orbit, or ejection outward into interstellar space. For an outer ice giant with a wide, loosely bound orbit, ejection is the more likely outcome. Neptune's path would stretch and open until the planet simply leaves, carried out of the solar system entirely, to drift alone through the galaxy from then on. On screen, distance from the Sun 10 AU, time to arrival 1 year. Nearing Saturn's orbit, the black hole's gravity begins reaching into the asteroid belt. Orbits there, already loosely held together, get pulled and reshuffled. Some asteroids are flung outward. Others are redirected onto new paths, some of which, by chance, now cross Earth's orbit. On screen, distance from the Sun 4.4 AU, time to arrival 5 months. This is where the scenario turns genuinely dramatic, because Jupiter is now close enough to be reshaped. A black hole does not need to touch a planet to affect it severely. Tidal forces, the difference in gravitational pull between the near and far sides of an object, do the work. We've actually watched a small-scale version of this before. In 1994, a comet called Shoemaker-Levy 9 passed too close to Jupiter, and the planet's own tidal forces pulled it apart into a chain of fragments before they struck the planet in full view of telescopes on Earth. A black hole exerts the same kind of stretching, just at a scale that can unravel a planet rather than a comet. As the black hole approaches, Jupiter's outer atmosphere begins to stretch, then stream away in a long, spiraling trail. This gas doesn't simply vanish. It settles into a flattened, rotating disk around the black hole, and as it compresses and rubs against itself, it heats up, glowing first orange, then a fierce blue-white, radiating far more light than Jupiter itself ever did as a planet. On-screen view from Earth, time to arrival 5 months. From Earth's night sky, this would be extraordinary and strange. Jupiter, a familiar bright dot for all of human history, growing brighter, then transforming into something new, a small, glowing disk visible without a telescope, outshining every star and planet we know. Meanwhile, the disturbed asteroid belt sends its first consequence toward us. An asteroid dislodged months earlier reaches Earth's orbit. On-screen distance from the Sun 0.9 AU, time to arrival 25 days. By the time the black hole passes near Mars's orbit, Jupiter has been entirely absorbed into that glowing disk of gas, no longer a planet, but fuel for a structure now orbiting the black hole itself. Having just taken in that much material, the black hole briefly produces jets, narrow, tightly focused beams of particles launched from its poles at close to the speed of light, visible even from Earth as thin, glowing lines against the dark. On-screen distance from the Sun 0.34 AU, time to arrival 9 days. Now closer to Earth than the Sun itself, the black hole's gravity begins to dominate our planet's motion. Earth's orbit distorts, curving toward the passing mass. Based on the physics of these encounters, ejection rather than capture is again the more likely outcome. Earth would very probably be flung outward, away from the Sun, rather than pulled in. As Earth swings past at close range, its sky offers something no human has ever witnessed. The warped, curved light of stars bending visibly around a dark, invisible mass. And as charged particles from the disrupted system interact with Earth's own magnetic field, brilliant auroras spreading across skies where they've never been seen before. On-screen near the Sun, time to arrival 3 hours. In these final hours, one more strange effect would become noticeable to anyone still watching from a safe distance. Close to a mass this concentrated, time itself runs measurably slower, a real confirmed consequence of gravity called time dilation. A clock near the black hole, if one could somehow survive there, would tick visibly behind a clock further away. It's the same effect at a vastly smaller scale that GPS satellites already correct for every day, orbiting a much gentler gravitational well. On-screen arrivals. The black hole reaches the Sun's former position. The Sun, no longer anchoring anything, has itself begun to spiral into a glowing disk of its own material, the final chapter of a star that had shone steadily for 4.5 billion years. On-screen, a new arrangement. What remains afterward would be strange, but not empty. Some planets, likely the innermost ones, disturbed early and gently, might settle into new, tighter orbits around the black hole itself, forming a small, dim planetary system around a completely different kind of star. Without sunlight, any such world would depend entirely on a different source of warmth. The same tidal flexing that keeps Jupiter's moon Io volcanically active today, stretched and squeezed with every orbit, could keep a captured planet's interior heated for a very long time, even in permanent darkness. The rest, Neptune, quite possibly Earth and others, would continue outward, no longer orbiting anything, destined to drift through interstellar space for the rest of time. Rogue planets, following the same lightless path the black hole itself once followed long before it ever found us. In fact, astronomers already suspect our galaxy holds billions of such unbound worlds, ejected from their own systems by encounters far less dramatic than this one, drifting now with no star to call their own. To be absolutely clear, nothing like this is currently approaching our solar system. Every rogue black hole we've found is moving on its own path, none of them aimed at us, and the odds of a close encounter within any human timescale are vanishingly small. But the physics behind every stage of this scenario, the gravitational tugging, the tidal stretching of gas into glowing disks, the ejection of planets, the bending of starlight, is real observed physics seen in other systems across the galaxy. We are simply, for now, far enough away to only imagine it.